All right, hello everyone, and thanks for joining me. My name is Matthew Hill, and today we're going to talk about how to derive the gamma constant from first order principles. I do apologize, I submitted a video a little bit earlier, a couple weeks ago, and there was no audio, so I decided now that I'm kind of home and with my computer set up here, I figured I'd just go ahead and re-evaluate this problem here. So this actually pops up, this question, specifically deriving the gamma constant, is in the HPS practice book. I've seen it a couple times. Not necessarily in old practice exams, feel free to correct me if I'm wrong, but it is a constant that gets used so often in this industry. It is definitely important to know exactly where it comes from and how we calculate that from the ground up. Because when we talk about the gamma constant, really it's a constant that is well published in all types of different units through Radiological Health Handbook, just any type of standards book. You can find this all over the place. And they're published because it really helps reduce the amount of time to perform exposure calculations for specific isotopes. So before we jump in on how to solve it, I really do want to just give a quick few words on what it is, its limitations, and how we use it overall. So just remember the gamma constant itself is nothing more than defining an exposure rate for an isotope that emits gamma radiations at the distance of 1 meter for an activity of 1 curie, and we're going to look at the exposure for a time of 1 hour. So really that's all it is. This is no different than calculating exposure under a very specific set of circumstances. And the way that we're going to do that is we're going to look at the characteristic radiations that are produced from the isotope at hand. So I believe the practice book is cobalt-60, and that has 2 gamma emitters. For this problem, we're going to look at cesium-137. And I do recommend for this exam, you should know cobalt-60 and cesium-137, the gamma constants for that. Just, it's a good number to have, and you'll come across it so much in the field. Just commit it to memory. And like I said, there's lots of different units. The one that I typically remember is R meters squared per curie hours. And for cobalt-60, you're going to get 0.33, 0.32 R meters squared curie hours. So that's what we're going to try to attempt to rederive here in this problem. So the way that you go about doing this is you need to understand for cesium-137, we know a few key things, right? You need to know the decay information. And this may be provided to you, in a schematic. I'll try to show a picture of that here as well, of kind of what you can expect to see. And if you know cesium-137, when we talk about the decay scheme, it actually decays by beta decay. It's a pure beta emitter, and that's actually, if you're doing part 1, that's a good thing to know. We don't detect the betas typically because there's a very nice barium-137 metastable state that it decays to, like 94% of the time. And then from here, we get a 662 keV gamma that's emitted. So when we talk about a gamma constant for cesium-137, we're really just tracking this barium-137 metastable state. As it decays, it has a half-life of about 2 minutes. We're expecting to see these 662s pop off. And that happens about 85% of the time. I think it's 85.1% overall. That is what we consider the yield. So that's what we're going to use for this question in particular. So real quick, when we talk about exposure, we're talking about Rankins. It's really important to remember what that measures. So the Rankine is the measure of total ionizations within a mass of air. So a few things, when we talk about Rankins, it really should be X-rays, photons, gammas only. And specifically, we're looking at that ionization in air. So the problem is we have decay information, which is going to tell us how much energy is emitted. And we're going to be looking at how much energy is emitted and absorbed within this air, but we need to be able to relate the actual dose rate to the exposure rate overall. And the way we do that is through the specific ionization constant. And for photons in air, it's about 34 eV per ion pair. And this is on the exam sheet, so just know if you're asked, this is at standard temperature and pressure, you'll have to say, hey, we want to figure out of that total energy that is deposited in the air, how many ion pairs are produced, and then from there we can relate this to coulombs per kilogram is kind of our end goal. How do we get back to coulombs per kilogram? Because that's going to help us get to Rankins overall. So all that to say, just remember cesium-137, It is a pure beta emitter. However, barium-137M, the daughter product, is what emits that 662 keV, and that's 85% of the time. We talked about exposure rate is strictly looking at exposure of photons. So gammas or X-rays, what's being produced. I guess in this case, because it's the gamma constant, we're looking at gammas only because we're looking at sources of radiations from a decay product, or a decay itself. Okay, with that, let's go ahead and actually calculate exposure. So to calculate exposure, we're going to use a formula that really has to deal with calculating exposure for isotropic sources. So ding, 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 that's an assumption. We're going to assume isotropic source. Make the graders happy. And to calculate the exposure rate, we're going to look at some activity S, averaged across the entire surface area of the sphere, right? So it's 4 pi r squared, times, in this case, we're going to be looking at the actual energy produced. So it will be a sum. So if you're going through cobalt-60, you'll have 2 gammas, right? So it'll be the sum of the first energy gamma times the yield, which is 100%, plus the energy of the second gamma times the yield, which is 1. So, but for cesium-137, there's only 1, so sometimes you may see this summation ignored. But we're going to look at that energy we just talked about and multiply that by the yield. Okay. From there, we're going to multiply by our mass absorption coefficient. And we'll talk about where we can find that. And then we're going to have to do a whole bunch of conversions over here, because we're starting out this problem more than likely in MeV centimeters squared per gram. Kind of looking at a few of this. This is centimeters squared per gram. We do have a meter squared. So we'll have to like really massage the units, because our end goal is to get this overall in coulombs per kilogram seconds, or in really hours if we can, because a coulomb per kilogram is actually the definition of a Rankine. So to get the rate, we'll have to eventually get this all into coulombs per kilogram. So bear with me as I go through with this. I'll try to get all my units just right and set up this calculation. But you need to remember right here that this is the actual equation for exposure. And from there, assuming you're good at your actual unit conversions, it's just a matter of getting the units right to have this pop out to the correct answer. So a few things. As far as mu-en over rho, if you're not aware, go ahead to go to Google, type in mass attenuation coefficient, air, and 600 keV, or 0.662 MeV, and more than likely the first link that's going to pop up is a link to NIST. NIST publishes all the mass attenuation and mass absorption coefficients for given media. In this case, we're going to be looking at dry air STP, and when we get that, it comes out to be about 0.03 centimeters squared per gram. That's helpful if you're practicing. This will have to be given to you. You'll have to have a chart, or it may just give you the value. So just remember, if you're in between two, it's probably best to go ahead and do a quick interpolation and find some linear interpolation between the two. So I'm not saying you have to do that. I know some folks that will just default to more conservative, but if you want to be 100% accurate or give the best answer you can, take a moment, interpolate between the two values, because more than likely you'll get 500 keV and 600 keV, and you'll have two values you have to pick between. But remember, in this case, we're talking about mu-en over rho, the mass absorption coefficient, dosimetric term. If we were doing shielding calculations or looking at shielding and we want to know like what thickness of material, that's when we would do mu over rho and go from there. So let's see, anything else that needs to be given? I think we'll be okay from here. So with that, let's go ahead and set up our actual equation. So x dot, coming back to this, is equal to 3.7 times 10 to the 10 becquerel, which is disintegrations per second, all over 4 pi times 1 meter squared. Remember, we're doing 1 meter, 1 curie, 1 hour. We're going to multiply this by our 0.662 MeV. Multiply that by our 0.85 yield. Okay, that's our summation term. And then we're going to multiply by our 0.03 centimeters squared per gram. This is our mu En over rho. Okay, technically that's our exposure. The problem is we've got meters squared over here, we've got centimeters squared, we've got grams. Remember, we're trying to get to coulombs per kilogram hours. And you'll see why with our actual conversion factors that we have. So let's do a couple quick changes. We want to go from MeV to EV. So that's 1 times 10 to the 6th EV per MeV. That's going to help us out here. All right. 0.85 is unitless. Let's get our mass absorption coefficient in the correct. So let's get that in meters squared. So we know that there are, for 1 meter squared, we'll have 100 centimeters squared. And we want to get that into grams into kilograms. Let's see what we got here. So we know that there are 1,000 grams per kilogram. Okay, that's going to help clean us up. So now we have our meters squared canceling out front. We have our centimeters squared canceling. That's good. MEVs cancel. That's good. Our grams goes to kilograms. So we should be left, and we'll clean this up just to help make that look a little bit neater. So bear with me. I'm going to do these calculations. Okay. So we're left with 4.97 times 10 to the 12. We got disintegrations up top per second. And so let's see what's left. We have EV all over kilogram seconds. All right, we'll continue this game of updating our units. So remember we talked about going from EV to coulombs. We're going to need the term the specific ionization constant. So we know that 1 ion pair is equal to 34 EV. So that's nice. Now each ion pair we're able to multiply by our elementary charge constant, which is provided. It's 1.602 times 10 to the minus 19 coulombs per ion pair. So that's good, we got that. And let's see, and we know there's 3,600 seconds per hour. Okay, I'm going to go ahead and do this calculation just for space so you can follow along. Okay, we're left with 8.43 times 10 to the minus 5. Units are looking much better, our seconds cancel. And we're now in coulomb per kilogram hours. All right, this is the last step. We need to remember that 1 Rankine is equal to 2.58 times 10 to the minus 4 coulombs per kilogram. Okay, so this last calculation should give us our R per hour. And what do we get? We get 0.327. And this will be an R per hour. All right, there you have it. So the last step is just to make the note that now that you've done the calculation, gamma in this case will be 0.33 R meters squared per Curie hour. And you're free to use this in gamma A over D squared for a point source or whatever you need to from there. So really what it comes down to is just calculating that exposure rate. Make sure you're able to calculate exposure rates, and moving forward you're able to scale that kind of using this gamma A over D squared moving forwards, hence why these are very well published across the sector. So yeah, if you have any questions, feel free to throw those into the comments, but once you do this once and you're able to do it for cesium-137 and cobalt-60, it really does not matter what isotope they throw at you, because they're going to have to provide the decay equation. And as long as you understand the specific ionization and how to go from energy deposited to coulombs created, really it just becomes a matter of conversion of units. So hope this helps. Happy studying, and thanks again for watching.